Okay guys, what we're going to look at is calculus, and we'll look at just the basic things that you can expect in your test with regards to calculus. And I'll just go through some of the theory, and then we'll look at as many examples as possible. Now, first of all, the idea of calculus is to look at the change of a graph. In other words, how is a graph changing over time? So, or a function rather, how are functions changing over time? Now, if we look at change, what we mean is that at one point I'm here, and at another point in time I'm there. So when x is here, then y is there, and then at some other point x is here, and then the y value is up here, for example. Okay, so if we're looking at the change, we're talking about the rate of change. In other words, how is y changing compared to x changing? In other words, how is y changing per unit that x is changing with? Okay, and when x1 and x2 are two distinct points, this formula would give me the average rate of change. Okay, so rate of change is comparing. So change is just how is y changing. Rate of change is I'm comparing it to something else that's changing. So x is changing and y is changing. So the question is, how is y changing compared to x? So you'll see that if this value increases, it means that the change in y is getting bigger, or the change in x is getting bigger. So for example, if x2 was here, but we had the same y value, look at the rate of change now. Now I'm dividing with a smaller number. Do you see? The difference between x1 and x2 is now smaller, but the difference in y is still the same. Alternatively, I could have maybe said, okay, well, my change here, but let's now see, instead of going to y2 there, let's say y2 is there. Okay, there's y2 now. Now notice again, this time I've got the same change in my x values, but my change in my y values are bigger. And in both of these times, compared to the original one I had here, the difference is the steepness. Do you see? The steepness increases either when my change in y increases or when my change in x decreases. Okay, now rate of change is therefore what we use, and we call it the gradient. The gradient. So when I have 2 points, I'm getting the average gradient between 2 points, because I've just been considering, I've put in the lines. I'm not talking about lines, I'm talking about a graph, and these points may all be on a graph. So for example, let's draw a graph through those 2 points here. Okay, notice that between these 2 points there's not a straight line. Between these 2 points there's not a straight line. The graph curves between them. So if you were to be an ant walking on this curve, at some point you would be walking steeper, going from this point to that point. At some point it's steeper, and at some point it's less steep to get from here to there than if you were to just go on a straight line. Look at this one between here and there. Okay, an ant walking here, okay, is an ant walking, he would be walking at a constant gradient. It wouldn't get any steeper or less steep. But an ant walking on here, he would first be walking very, very steep. At some point, he would actually be walking horizontal, and then after some point, he's walking downhill. Do you understand? But on average, his steepness and this one's steepness is the same. Okay? Does that make sense? If I'm talking about average gradient, it's just between 2 points, a straight line, while instantaneous gradient is now the gradient that I would have at a specific point. In other words, if I were to place like a book, I like to use my bald head as an example. If I place a book or straight line against my head, I can't change the direction, because if I wanted to change the direction, it would touch a different part of my head. Do you understand? So do you see at this point, this thing is too soft, I need a book. At any point on my head, it has a specific gradient. It can't have any other gradient, because if I turn it, it touches my head at a different place. Do you understand what I mean? So at this point, if I put a straight line at just going through that point, it will have a fixed gradient. And I could think of it as a steepness. Okay, and now the question would be, is how can we get a gradient of a point? Because my formula for gradient is change in y. Now the change in y is my x2 value substituted in f minus my x1 value substituted. These give me two y values, isn't it? Okay, divided by the change in the x values. This is the formula for average gradient. It's that formula. It's just my change in my y values divided by my change in my x values. But now I don't have 2 points. Okay, so what we do is we say, okay, well, let's assume we do have 2 points. Okay, but they're equal. So this is how we're going to do it. We're going to say, okay, we have 2 points. Here's my 2 points, but the second point is going to be movable. I can move x2, and I'm going to move him closer and closer towards x1. And as it's now going closer, look what happens to the gradient. So I want to know that, let's say the gradient at that point, let's use pink. I want to know what is the gradient at this point. The gradient at that point there. So I say, okay, well, let's take any other point after this point. We get a gradient. Now we look at a point a little bit closer to this one. So let's take that point, for example. He's a little bit closer. So now I'll go there, look at the average gradient now. What do you notice? This original gradient was in the same direction as that one, but they weren't really close, isn't it? But when I came closer, my new gradient became a little bit closer to this one. You see? Now if I choose a new value, there, notice what my average gradient now would be. There's my average. Do you see I'm getting closer and closer to the correct answer? Okay? So if I take a new value, I'm getting closer. The closer I'm getting here, the closer my gradient is becoming to the gradient I have at that point. Okay? So the problem is I can't get to it, because look what's going to happen. If my second point is equal to my first point, I'll have 0 in the denominator. You see that? So I have x2 minus x1, and I have fx2 minus fx1. And the way in which we do this, the way in which we look at one number approaching another number, is with the concept of limits. So we're saying x1 tends to x2. I should have actually done it another way around, because this was x2. It doesn't really matter. The point is the two numbers are getting closer and closer together. Okay? And when they actually get to each other, they can't get to each other because they're 0, and then I have a 0 in the denominator. So what we'll do is, whatever this expression comes to, I can't just substitute the two values. I have to first take this fraction that I have here and simplify it. Once I've simplified it so that I don't have the denominator anymore, then I can substitute because I don't have a 0 in my denominator. Let me show you. Morning, Michael.
Morning.
How are you today? I'm great, thanks. Sorry, MK, how are you? I'm good. Good to are you well? That's great. Okay, so let's have a look at just changing this a little bit. What we're going to do, instead of talking about the change between x and y, let's just say that the change between x is going to be the letter h. In other words, h is just representing the distance between these two. Okay? Which means this one will still be x, but then this one, this point, at this point, this will be x plus h. Does that make sense? Because this is h, if this is x, then this point here is x plus that length. Does that make sense? Understand it?
It's x1, x2, or x1 plus x1.
So I'm instead of using x2 now, I don't want to use x2. I want to use just x. That's this point. x1 is going to be called x. The distance between x1 and x2 is going to be h. So x2 will be x plus h. You get that? Okay? So if that's true, look how my function changes. First of all, x2 must be replaced with x plus h. Still the limit. If we say x1 tends to x2, what we're actually saying is that x1 minus x2 tends to 0. Does that make sense? It's almost like an equation. x1 tends to x2. So I just subtract x2 on both sides. That means x1 minus x2 is 0. Is tending to 0. So in other words, and x1 minus x2, that's the distance between them. That's h. So in other words, this limit changes to the limit of h tending to 0. If x2 becomes fx plus h, because x2 is now x plus h, and x1 is just x. And then in the bottom I have x2, which is x plus h, minus x1, which is just x, so it's minus x. So I've got x plus h minus x, which is just h. And this is now called the gradient at a point. Okay, because what this formula gives me is it gives me the gradient at that specific point. All I need is the value of x and the function formula f of x. Any questions so far? Okay, now the gradient at a point is called the derivative. Does it make sense? And we use this the notation we use is a little f with a little accent that represents the derivative, or it can be dy over dx. Notice the relationship between this and that. This is a Greek letter D. Delta is a Greek letter D. In maths, we use Greek letters to not always, but in this case, we use the Greek letter D to represent difference. We use the lowercase d, this is a Roman letter D, to represent infinitesimally small difference. Do you understand what I mean when I say that? In other words, the change in dx is infinitesimally small, almost 0. So what is the change in y when there's almost no change in x? And what? And yeah, the relationship. Does that make sense? Don't get a lot of hoo-ha's for that. That's fine. Okay, now if I wanted to go and find the gradient of a function, in other words, the derivative, I'm trying to find the gradient of a function or the derivative, I can now use this formula. Let me show you. So let's look at a straight line. We all know the straight line formula is mx plus c. Which variable represents the gradient? M. In a straight line, is the gradient constant or is it constantly changing? Constant. The gradient, the steepness of that graph doesn't change. Okay, so let's quickly look at using this formula to find what would be the formula for the gradient. Well, you should know the formula for the gradient is constant. So it should just be m. But let me go and prove it for you. So we have this formula that the derivative is fx plus, the limit, sorry, don't forget your limit, h to 0 minus f of x over h. We have that. Okay? And now we'll substitute these values into our formula. So there's my f value now. So I'm going to substitute. So I put in m x plus h. So notice where there used to be an x, I now replace it with x plus h. And whenever I do that, personally, I put brackets. Instead of the x, I put brackets, and whatever is inside there, I don't care what's inside there. I just substitute that into the brackets where I used to have an x. Is that okay? And then I still have the plus c. So look here, I've got the same thing that I had up here, but just instead of the x, I put an x plus h, because that's what this is saying. F is saying, instead of having an x, put an x plus h. Minus, and then this one is just f minus f of x. Now, because there's a minus, I'm going to also put it in brackets. It's what a lot of people forget, this bracket, and then their signs work out wrong, and some won't work out. Oh, and please don't forget your limit, h. Now, what we want to do with the limit, and I didn't say this, but hopefully you guys got it. The way that we will evaluate the limit is by substituting. Not always, but at school level, we only do limits that involve substitution. Okay? So I would like to substitute h in there, but I can't. Because h is in the denominator, and if I make it 0, I'll have an undefined expression. Whenever that happens, the first thing I'm going to try and do is simplify my fraction to get rid of that denominator. Make sense? So let's try and do that. So I'm going to simplify this thing. I would love to substitute, but I can't. I'm not allowed to as long as it makes my denominator 0. So I'm going to simplify. My m multiplies in. Since I can't substitute yet, I must keep my limit. I multiply in mx plus mh plus c minus mx minus c over h. Okay, and now you'll notice that some of your terms in the numerator doesn't have an x in it. They must always cancel out. If they don't, you've made a mistake. So look, my mx minus mx cancels out. My c, everything that doesn't have an h must cancel out. I'm missing some. Oh no, I don't. My c and my c cancels out. So in the end, I only have mh over h. Now this is my point. If it didn't have an h, if there was a term that didn't have an h, I still have to divide that term with h. But now, my only term left has an h, and the h's can now cancel. Does that make sense? So I'm now only left with m. I've got nothing to substitute h with, so I substitute nothing and get rid of my limit. All I'm left with is m. Let's quickly look at a parabola. Parabola is ax squared plus bx plus c. Okay. A parabola looks like this. And what do you notice about this one's gradient? You can tell me a little bit about its gradient. Its gradient is? No, this one's gradient is actually negative.
It's not constant.
It's not, sorry, the gradient's not negative. The gradient at some points are negative.
Oh.
Because here, if I'm walking here, thank you, Ms. Sunday, that's what I wanted. It's changing. At different points in this graph, I've got different gradients. Here, my gradient is downhill. Here, my gradient is horizontal. There, my gradient is uphill. And as I go along, as I'm walking along, my gradient is actually getting steeper, 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 steeper. But here's a very interesting thing. That the gradient of this thing is, let me rather say, the gradient of the gradient is constant. So the gradient is changing, yes. I don't know how to say this, but the gradient of the gradient is constant. I'll show you now what I mean. What I mean is this thing, sorry? The second derivative is constant. Now, what do I mean by that? I mean that this thing's gradient, if I were to work out its gradient, it will be a straight line. And the gradient of a straight line is a constant. Do you understand what I mean? The gradient of the parabola is a straight line, but the gradient of the straight line is a constant. So the gradient of the gradient is a constant. Do you understand? Okay, so let me go and prove that to you, that the gradient of this thing is a straight line. How will we do that? I'll use this one, dy over dx. So dy over dx, and here's my formula, the limit. Now what I'm doing now is finding the derivative, finding the gradient, the instantaneous gradient. Remember, that's what the derivative is, the instantaneous gradient. I'm finding the derivative at a point, from first principles. This is what we call it. Finding the derivative from first principles means I use this formula. When they give me my formula in y, I will use this notation. If they give my formula in dy dx, my formula in y, I use this. If they give it to me in fx, then I'll use f derivative x. Okay, but nevertheless, here I still have to use that because that's my formula. But we know what we mean when we say this. And so let's go substitute. Another way you could have written it is also y with an accent. It's also another symbol for the derivative. Okay, but let's go and find f of, and then here. What does this mean again? How would I use this? Yeah? But more importantly, you put a bracket, and in that bracket you put x plus h. Okay? I promise you guys you're going to regret not putting a bracket. So what do? Here's my expression. Everywhere where there's an x, I'll put a bracket with x plus h in it. So here's an x. I'll put a bracket, x plus h. But this x had a square, so my bracket must get a square. Plus b. Then my bracket with x plus h. Plus c. And then minus, and again remember, the important part, when you subtract something, put the thing in brackets that you're subtracting. Ax squared, just so that you don't mess up your signs. Now, can I substitute my h? Why not, Taban?
Because the denominator
denominator will be 0. So I must first simplify this thing. And it must simplify so that every term in the numerator has an h. If it doesn't, I made a mistake. So let's go. As long as I can't substitute, I keep my limit. Here I've got ax squared plus 2xh plus h squared plus bx plus h plus c minus ax squared minus bx minus c. Everyone okay with that? This should be grade 10 work. Just simplifying that. Okay, now I multiply in my a. So I get ax squared plus 2axh plus ah squared plus bx plus bh plus c minus ax squared minus bx minus c. So as I promised, everything that doesn't contain an h must cancel out. There's ax squared, there's minus ax squared. It's got an h, that's fine. It's got an h, that's fine. This one doesn't have an h, so he must cancel. There's his cancellation. There's my c. C doesn't have a h, and there's the negative c. They will all cancel. So that in the end, I'm left with 2axh plus ah squared plus bh, and that's it, divided by h. Now remember, when I have a fraction, and in my fraction my numerator has more than one term, but my denominator only has one term, then I distribute. The distributive law of division. Okay, so every term must be divided by h, and then I will have this term. When it's divided by h, the h will cancel, so I'll have 2ax. This term, when it's divided by h, I will have one of the h's cancel, so I'll have plus ah. This last term, the bh, the h's will cancel, and I'll have b left. My denominator has now divided every term, so I don't need the denominator again. Make sense?
Peter?
Yes.
Can you do it another way?
How would you could how would you do it?
You take out an h in the top, and then just cancel the h with the bottom.
That's perfect.
That's what I usually do.
That's a perfect way of doing it. Okay. Technically, this is a more consistent way of simplifying fractions, because when we simplify a fraction, if there's more than one term, top or bottom, I factorize and cancel. Okay. The only reason why I don't, well, I could have suggested it like this as well. The reason why I don't is so that I can show you the reason why we need every term to have an h in is so that the h can cancel into every term. But we could say the same thing for factorizing. The reason why I want every term to have an h in is so that I can take an h out as a common factor to cancel with the bottom h. Make sense? Okay, so if you don't have that, then obviously you've made a mistake somewhere. There's one exception. I'll look at that. Now, when I substitute, am I allowed to substitute my h with 0 now? Yes, so now I just get 2ax plus b. And this has the form of mx plus c. Do you see? Mx plus c. So the derivative of a parabola is a straight line. Okay. Where this parabola has a turning point, what does it tell me about the gradient at the turning point? 0. That's what a turning point is where I'm stopped. I'm not going up anymore. I'm starting to go down, or I'm not going down anymore, I'm starting to go up, whichever way. But at that point, I'm not going up or down. Does that make sense? Which means I'm going straight. If I'm not going up or down, I'm going straight. So my gradient at the turning point is 0. Now look at how cool that is. Here I've got the gradient. If I make my gradient equal to 0, look what I get. 2ax plus b is equal to 0. 2ax is therefore equal to negative b, divided by 2a on both sides gives me that x is negative b over 2a. Does that look familiar?
Yes.
Okay. So guys, don't go and try and remember this formula. Just remember this one thing. The derivative is the gradient. So if I want to know where is the turning point, all I need to know, well, that's where the gradient is 0. So that's where I make my derivative equal to 0. Now, obviously, this is a longer method to find the derivative, and there is a shorter method which all of you know. Okay, I know that's probably the only thing you know in calculus is how to find the derivative of a parabola. Okay. So you shouldn't have a problem getting here. And just make that whatever. So in other words, if I wanted to find the turning point, this is just the x value though. Okay. So that just gives me where I'm turning for x. How will I find the y value? Into what?
Into the original.
Or into the original, because this is the original. I want the y value associated here, this y value, which means I'm going to substitute into the original, not the derivative. Okay, so once I get that, I will, and I like to call this my p value, okay, because the turning point is the point PQ. I like that. And so to get my q value, the y one, I'll just take whatever I found here, in other words, negative b over 2a, and I'll substitute that into to get my turning point. So there's a lovely help for you. But let's now see. Again, if I find the derivative of the derivative, we saw before, the derivative of the derivative is now the gradient of this graph. And this graph's gradient is 2a. So the second derivative is 2a. This is how I write the second derivative. Or if I wrote it in my other notation, it is d squared. Is it like that? I think it's like that. The d gets squared, second derivative, and the x gets squared. It's a little bit different. It's not y squared. But this is usually what we will work with. Okay, so what else did I want to show you? Okay, let me just show you quickly a slightly more difficult derivative from first principles, and that is if my function is a parabola. I'm going to use the easiest parabola because I'm lazy, but you can go and practice it with the more complex ones. Okay, so let's find the derivative from first principles. So for this one, we'll take the formula, the limit as x tends to, sorry, not x, as h tends to 0 of fx plus h minus fx over h. And so, what does this mean again, MK? So my function is this, so I keep it with that, but instead of the x, I put an x plus h in a bracket. Minus, and then on this one, 1 over x, divided by an h. Now I can't substitute yet because of the 0 in the denominator that I'll get, so I'll keep my limit there. Okay, now this I must simplify. How do I simplify when I add two fractions? I think you're more or less there now, aren't you?
Yeah,
what do I do?
You basically find a common factor.
You find not common factor, a common denominator.
Common denominator.
That's it. So you know.
X and then x plus h.
Excellent. So this must be x, needs an x plus h, and this one needs an x. I can't just.
Then you for the first one you say 1 and then x plus h.
Just no, this one, I multiplied the bottom with an x, so I must multiply the top only with x.
Right.
This one I
That
multiply.
is an x plus a.
Yeah. Well done. So that when you cancel, you still have the originals. So you haven't changed anything. You've changed something, but not the value of the expression, because they will simplify. And now we can add. So again, the whole aim is if you can't get rid of this h in the denominator, either you can't do algebra or you've made a mistake. So now if I were to add these two things, in the numerator I've got a fraction, so I'll keep it like that. Well, that's my denominator, but in the top I now have x minus x plus h. X minus x plus h. Now then minus must then multiply in, so it becomes x minus h. And there you see once again, in my numerator, everything that doesn't have an h cancels out. X minus x, and I'm left with negative h. In the bottom, I'm left with h. Now, whenever we have a fraction divided by, so let's change this one to a fraction divided by a fraction. One of my first students taught me tip times. Then I tip and time. Well, he didn't teach me tip and times. He taught me the word tip and times. And I multiply with the inverse, 1 over h. And there we can see that they cancel. So that all I've got left now is the negative 1 times 1. And in the bottom, this is just the 1, I've got that. So now, is h still in the denominator? Yes. Can I replace h with 0 then? You can, because it doesn't make the denominator 0 by replacing this h with a 0. Do you understand? I'm only allowed not to replace if it causes my denominator to be 0. So for example, if I have something like x minus 2, is x allowed to be 0? Yes. X can't be 2. It's not about the denominator not having a 0 somewhere. It's about the denominator not being 0. So so in here we can replace that, because then I'll just have in the bracket, I'll just have x plus 0, which is x, and then I've got a square there. So once I replace, I don't put my gradient, so I've got the negative 1 in the top and x squared in the bottom. Okay, let me show you one last thing. I want to show you, what's this, the Pythagorean Triangle, I think is that, it's called that, something like that. It looks like this. It starts with a 1 in the first row. In the second row, I've got 1 and 1. I always start my row with 1. The next row is a 1, then I add these two together and I get a 2, and I always end on a 1. The next one starts with a 1, I add these two to get a 3, I add those two to get a 3, and I end on a 1. You get where I'm going with this? Okay, so the next one is a 1, this one is a 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Now notice everything follows a pattern. 1, look here, 1, 2, 3, 4, 5, 6, 1 plus, so this is 1, 3, 6, 10, what do you think is the next number? Yeah, because here I'm adding a 2, here I'm adding a 3, here I'm adding a 4, now I'm going to add a 5, so this is 15, okay, then 1, 4, 10 is, this one is 20. This one is the arithmetic sequence. This is the quadratic sequence, and this one will be a cubic sequence. We don't do cubic sequences, but this one will be a cubic sequence, and then the next one will be a pentic sequence, in other words, x to the power of 5, whatever. But this one will be 15, and this one will be 6 and 1. Okay. What I want to show you is that this gives you the coefficients when you multiply out x plus y to the power of 0, to the power of 1, to the power of 2, to the power of 3, to the power of 4, to the power of 5, to the power of 6. Okay, so this one, if I have it to the power of 4, it will become x to the power of 4 plus, and now x gets 1 less, but y gets 1 more. So the coefficient is 4, x 3, y 1. The next one, the coefficient is 6, x 2, y 2 plus 4, x 1, because x is decreasing, 4, 3, 2, 1, and y is now 1 more, 3. And then the last one is plus 1, y to the power of 4. There's no more x's left. You see? Okay. So, and it would be the same for something like x plus, let's say 2. If I were to put it to the power of 6. My first term would be x to the power of 6 with a 1 coefficient. Then it would be plus 6 times, okay, the 6 times x plus, now 2 also gets in, so because now instead of a y I have a 2 now, so it's 6 times 2 is 12, x to the power of 5. The next one is 15. So it's plus 15, but the y value is squared, so the 2 is squared, so it's 4. 15 times 4 is 60, x to the power of 4. The next one is 15. Next one is 20. Y is now to the power of 3. 2 to the power of 3 is 8. 8 times 20 is 80, x to the power of 3. Plus, now, yeah, that was 3. Now x is to the power of 2, y is to the power of, so notice here the x and the y coefficients always add up to that. 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, and 4. So if x is 2, it means 2 will have an exponent of 4. You get it? So 2 to the power of 4 is 16. 16 now gets multiplied with 15, my next coefficient. 16 and 15, 80, 75 is 150, is it? 16, no, it's less. Yeah, it is. 100, no, it can't be. 15 times 10 is 150. 15 times 6 is 90, so it's 240. Okay, plus now x to the power of 1. Y is to the power of 5. 2 to the power of 5 is 32. 32 times 6 is 180, plus 12, 192. And plus my last term is just 2 to the power of 6, which is 64. Okay. Now I'm showing you this because I want to show you here in this expression if this one, instead of y, so if, for example, if I had x plus h for that first one, just as an example, my first term will not have an x in it. Do you agree with me? Sorry, will not have an h in it. My first term 1. Okay, it would just be h to the power. So if he was in this expression, if he doesn't have an h, he must cancel out with the other side. Okay? The next term will have an h in it. 1h. X to the power of 3h. It doesn't matter now what's in front there for now. Okay? He will have an h in it. The term after this one, whatever the coefficient is, will have 2 h's. And this will be the case no matter what that exponent is. So if I've got x plus h to the power of n, my first x will have the same exponent. My next x will have 1 less, but it will have 1 h. The next x will have 2 less than it started with, and I will have 2, and this will go on until I have n h's and no x's. Do you understand where I'm going with this? Now the reason why I say that is because when I subtract from this thing, so imagine now I've got fx is equal to x to the power of n. Then fx plus h is equal to x plus h to the power of n. Now when I simplify this expression, I get something like this. Look at the coefficients just now. But I'm going to subtract from it, because of this I've got fx plus h minus fx. So I'm going to take this expression is fx plus h, and I'm going to subtract fx, which is just equal to x to the power of n. So in this expression I will cancel the one term that doesn't have an h. Are you with me? Because I'm going to subtract x to the power of n. So the one that doesn't have an h will cancel. The rest all have h's. But now the rest are all going to be divided by h. So if I divide every term with an h, then from here on onwards, all of the terms have an h, so I can do that. But my first term will not have an h in it. This one. Because he's the only one, his h got cancelled. He only had one h. The rest will still have an h. But now, for the rest, when I substitute my limit h tending to 0, all of these guys will become 0 because they will have an h in. The h is a 0, I'll multiply with 0 and they'll get gone. So in the end, all I'll have left is this thing and whatever his coefficient was. You see where I'm going with this? So all I need to know is what was his coefficient. Well, let's go there. All I'm really concerned with is what was this second term's coefficient. Because he's the one term that only has one h. His h is going to get cancelled, so he won't have an h when they multiply with zeros. He's going to be the only survivor. Makes sense? So that is the one whose coefficient we're concerned with. And what is his coefficient? Well, if I go down here, I'm looking at the second row. I want to get the coefficient for that guy. This is n. If my exponent is 0, I don't have a second term. If my exponent is 1, my second term's coefficient is 1. If my exponent is 2, my second term's coefficient is 2. If my exponent is 3, my second term's coefficient is 3, etc. So if my exponent is n, in other words, if I have, let's change color, I'm sick of this pink. If my exponent is n, my first one I know is just x to the power is 1, according to this. My first term's exponent, coefficient will always be 1 to the power of n. My next term, what will his coefficient be according to Pythagoras' triangle? The Pythagorean triangle. It would be?
N minus.
No. Look, if my exponent is 1, the second term coefficient is 1. If my exponent is 2, my second term coefficient is 2. Look, x plus y squared is x squared plus 2xy plus y squared. My second term's coefficient is equal to that. If I have x plus y cubed, I get x cubed plus 3x squared y1 plus 3x y squared plus y squared. My second term's coefficient is 3. You see that? There's a relationship between my exponent and my second term coefficient. They're the same. So in other words, this thing, I'm only concerned with the second term because my first term will be minused. My second term will only have n x to the power of n minus 1 and 1h, and then the rest will all have more than 1h. And it doesn't matter what's going to happen there. But what I want to show you is that in the end I'm going to, this one and this one will cancel. The h will cancel with everyone, will have 1h left except for this one. So in the end, once I substitute my limit of h tending to 0, only one term will not be cancelled, and this will be that term. And I did all this effort just to prove to you that if I have an expression x to the power of n, the derivative of that expression is the second term after the h was cancelled, which is n exponent and x with one less x than it started with, n minus 1. So it looks like, and this is the rule you guys do, it looks like this exponent was multiplied to the front and 1 was subtracted from it. It does look like that, and you can use it like that. It's just like you use the thing that when I've got a plus on the one side, I take it to the other side and it becomes a negative. It looks like that, but that's not really what happened. That's just what it looks like happened. What really happened was this derivative formula. The first term was cancelled, the second term h was cancelled, and so only the second term was left, who had the exponent as his coefficient, and he had one less exponent than the first term. Make sense? Great. And this becomes the foundation of polynomial derivatives. Not really polynomial derivatives, it's called the derivatives of powers. In other words, if I have this expression, I have my x as base and any exponent. Then I multiply the exponent to the coefficient and subtract 1 from the exponent. You guys get that, huh? That's not difficult. Now, guys, when we ask you in the exam to prove from first principles or find the derivative from first principles, you have to use this limit of fx plus h. You guys get that? I think you guys are fine with that. When I give you an expression like this, and I say find this thing's derivative,
That's 712.
yeah?
This is 712.
Yeah, minus 12. If I ask you to find this thing's derivative, okay, you don't have a rule to find this thing's derivative. You have a rule to find this thing's derivative. This is not that. And you can't you can't go and find the derivative of the top and the derivative of the bottom. Okay, you have to, before you can find the derivative, get every term to look like that. And you don't have terms here. You have a single fraction. So you have to simplify that fraction. Michael, tell us again, how do we simplify fractions?
Find a common denominator.
No, that's how we add fractions. I know you're busy with that.
Yeah.
How do I simplify fractions?
Simplify.
A fraction. Factorize.
Oh, yeah.
Single fraction. So I factorize. That's what I'm going to do. X minus 4x plus 3 over x minus 4. Now I see this cancels, and so in the end the thing I'm going to factorize is this thing. It's not factorized, derived, finding the derivative. So dy over dx is now equal to 1x. Okay, sorry, not 1x, just 1. Why 1? Because let's have a look at it. This is x to the power of 1, and this is x to the power of 0. So if I take the exponent, multiply it to the front, in the front is a 1, so I get a 1. Now the x, I must subtract 1 from the exponent, so this becomes x to the power of 0. In this one, I take my exponent, which is 0, and I multiply it to the front, which gives me 3 times 0. Even though I get 0, even though my numerator now becomes -1, my coefficient is 0. So this term cancels completely. So that I'm just left with x times 1 times x to the power of 0 is just 1. Plus 0 times whatever on that side would be 0. So this whole thing, if I find this thing's derivative, it will look like that. What does it tell you? If I draw this graph, what type of graph is this?
Is it a straight line?
It's a straight line. It doesn't look like a straight line. It looks like a parabola divided by a straight line. But in the end, when I simplify it, it's a straight line. mx plus c. So the gradient must be constant. It has a constant gradient of 1. The interesting thing about this straight line is it's not a continuous straight line. What I mean by that is the original function x was not allowed to be 4. So when I draw this as a graph, when x gets to 4, I must have an open dot. So it's not continuous. Continuous doesn't mean I can draw it without lifting my hand. It's again what it looks like. But this thing I can't draw without lifting my hand, because when it gets to 4, I must jump it. I must exclude 4. Okay. So technically, when you find the derivative, you should actually just say there 4x not equal to 4. Just from the beginning, we had that condition. X is not allowed to be 4. Even when I simplified it here, I should have said, but x is not equal to 4. I simplified it, but my original function had a condition in it. X was not allowed to be 4. So just because I simplify it, doesn't mean now x is allowed to be 4. Okay. I've removed the discontinuity. That's what we say. Okay. Sorry, guys. Okay, so this in your exam, this is a very typical thing. I've shown you 2 things that you can for sure expect in your exam. Finding the derivative from first principles. And the derivative from first principle is what we call a routine procedure. Okay, it's a level 2 type question. Your exam consists of 35% of level 2 type questions. Okay. But level 2 can be divided up into 3 types: easy, medium, and hard. This, I would define this. Where is it? This one. I would have defined this as a medium to hard routine question. It's not an easy one, but it's routine. Just following a routine. You get it? This, what I showed you now, is a medium if I just gave you this, y is equal to 2x squared minus 4x plus 1 over, no, not even, plus 1. It's just something like that. And I ask you for this thing's derivative. That's easy. That's an easy routine. Easy routine. Okay. What I showed you now, when you have to first simplify, would be a medium routine. It's still routine. The routine is get it into a derivable form. Derivable form means every term is on its own. It's not being divided by anything. It's on its own. It's got its own unique exponent. Okay? And so that's the routine procedure, but this would be medium because there's just this extra step of factorizing to get there. Do you get that? So let me now show you the next. You get 3 levels in your exam. Level 1 is knowledge. Knowledge would typically be this question asking for which value is this expression not defined. When x is 4. That's a knowledge question. Something you can just read it off. You just look at it and you know. Okay. Knowledge is typically what is find the asymptote for this expression. Why is that a knowledge question? Because you can just look at it. You should look at it and know what the asymptote is. Okay. If I give you a mark for a formula, that's a knowledge question because you're getting a mark for knowing a formula. Do you understand? So that's knowledge. In your exam, 20% of your exam will be knowledge questions. So level 2 is routine. In your exam, okay, my exams are different. My exams, I only put 15 knowledge questions and 30 routine questions. But routine questions make up 55. The first 2 levels make up 55, which means, guys, you should get 55 at least for an exam without even studying. Okay? Because you should know these things. Like it's what you should know about maths. It's what you should know, the routine questions. Now we get into level 3 questions, which is your complex procedures. Now, a complex procedure, the one we just did, borderlines complex procedure. It doesn't mean a complex procedure is difficult. We don't use complex in that sense. It can still be easy, medium, and hard. The one we just did can almost be an easy complex question. Complex just means you can't just go ahead and do what you want, what the routine procedure. You first have to change the question a little bit before you can do your routine procedures. So, for example, a good example of complex procedures in this topic looks like this. Find the derivative of 2x minus x squared over the square root of x. Okay. Now the reason why this is complex is because it involves multiple routine procedures. Okay. Another topic that can maybe be complex is when you encounter something that you've not encountered before, although that might be level 4 as well, which is problem solving. But for example, if I ask you to find the inverse of y is equal to ax squared plus 2x. If I ask you to find the inverse function for that. Now you know that to find the inverse, I swap x and y around. X is equal to y squared plus 2y. But now you must solve for y. That's the next step. And this is just not a routine. Usually we didn't have this term. So usually it would have been easier. I would have just taken the square root on both sides. Now it's not going to work. Plus minus square root on both sides. So what must we do in this case? If you factorize, you still have y, and then you have y plus 2 is equal to x.
No, not that. Before that, at the first question, y is equal to x.
No, but then you just get this with, instead of this being a y, it would be an x. You get the same expression. You can see why it's complex. It's not difficult.
Oh, I know. I think you can multiply by 2 and then multiply by 2 and then minus by 1. Then you do the same.
Where? There? Where?
Yes, yes.
Multiply.
Y,
Yeah.
multiply by 2.
This y.
Yes, we do what we normally do. We say yes, y.
I'm not finding the derivative.
Okay.
I'm finding the inverse.
The inverse. Oh,
So inverse means I swap x and y around,
okay.
and then I try and solve for y. That's the 2 steps to do inverse. That's the routine procedure. But here we get to a kink in the cable. Okay? Now, most of the times it would be a problem solving question, because now I've got a problem. How do I solve for y? But because I've shown you guys actually how to do it, when we did the inverse, it's not problem solving, it's complex. Because it's not a problem anymore. You don't have to figure it out. You just have to remember how to do it. I won't show you now. You have to go figure it out. Okay? In this sense, we know what to do. We know we must get each term. I'm not allowed to have anything in the denominator. I must have each term by itself. I need a base x and an exponent. And so to do that, what will I do? Paulina, what would you say? Excellent. I'll divide every term by the square root of x. Can I find the derivative now? Not yet. What can be a next thing? It's a good one?
Change the formula for square root of x. Is it 1 over x?
No, it's not. Guys, this is unacceptable if you don't know that the square root of x is x to the power of a half. Okay, this is fundamental. X to the power of a half. This one? X to the power of 3 over 2. So square root of x is equal to x to the power of a half because it's 1, and a square root means I'm dividing the exponent, and it's a square root, which means I divide the exponent with 2. I divide the exponent. Square root means dividing the exponent. Okay, next. Masande?
No, you simply divide by x.
Yeah, but how do I divide by x? Do I just cancel the x's?
No, don't cancel that.
What do I do?
I say x minus x equal 1 minus x half.
I'm sure this is what you mean. So you say 1 minus a half.
Yes.
You subtract exponents. Okay? So 1 minus a half is a half. This is 1 and a half. Minus a half is just x to the power of 1. So 3 over 2 minus 1 over 2 is 2 over 2. So that's x to the power of 1. And here, Taba?
I think it's going to be just x to the power of minus half.
Thank you, to the power of negative a half. Why negative a half? Because there's actually an x there to the power of 0. There's actually no x's. So why negative a half? Because it's 0 minus a half. It's negative a half. Can I find the derivative now, Paulina? Yes. Yay! Okay, so I find the derivative. I'm going to use this notation, whichever they want. Okay. Now I can multiply the coefficient with the exponent. So a half times 2 is x. Subtract 1 from the exponent, which it used to be a half. It's now it will be negative a half. Half minus 1 is negative a half. minus, this one will just be 1, because 1 times the negative 1 is 1. 1 minus 1 is 0, so I've got x to the power of 0, which is just 1. And this one becomes negative. A half gets multiplied in front, x, and its exponent, instead of being negative a half, becomes negative 1.5, which is 3/2. And now, most of the time you can leave it like that. Sometimes they ask you to leave positive exponents, positive and no fraction exponents. So then we just have to go back. Just like here, we know, we saw here that this was 1 over square root x. So this is 1 over square root x. The negative means it's 1 over. The half means it's square root. Minus 1, I can leave like that. This one minus. Now, since I already have a 2 in the denominator, in the top I've got nothing, just a 1. So minus a 2 in the denominator. This divided by 2. I know the negative means my x is also going to be in the denominator. The divide by 2 means I've got a square root, and the numerator of that square root is the power there. Okay, guys, you have to practice this, because I can promise you, like, I'm giving you what's in the exam. It might be this very question. I don't know. I haven't seen that yet. But there will be a question like this always in your exam. Well, I should refrain from saying that, because but this is typically a complex question. So what a complex question usually does is it takes different themes and combines it. So here, for example, we took the theme, the grade 11 theme of surds and fractional exponents and factorizing and negative exponents, a bunch of themes, as well as then in the end to find the derivative. And that is why it is complex. I wouldn't say it's complex difficult. It's not difficult, but it's maybe complex medium. Okay. Okay, but that's basically as far as we're going to go with derivatives themselves. That's not the end of calculus. We'll now use this to go and help us with a bunch of stuff, even for you physics guys. There's awesome tools in calculus, because remember, what's acceleration? Acceleration is the rate of change. Velocity is rate of change. Anything in physics that involves rate of change, you can use derivative. Okay, because the derivative is the rate of change. You just need. Okay, so we'll look at all that just now. Just one more thing, one more notation that I didn't mention is something like this. Okay, so just in this, people don't know how to use this notation. This is asking you, find the derivative in terms of x. So in other words, x must be that base. Okay, if it looked like this, dt, it means that find the derivative in terms of t. So if this was an x t squared plus y t, you treat x and y as if they're constants. Do you understand? I'm finding the derivative in terms of t. I'm using t and using its exponents to multiply. The rest are just constants. So for example, and now when you find the expression, the moment you find the derivative, sometimes you must simplify it first, then you'll keep the dt. For as long as you're working inside, you keep the dt or the dx, whatever it is. But the moment you find the derivative, the dt is gone, because the dt says find the derivative of inside. So if you have the derivative, you don't put the dt in front, because then you're saying find the derivative of inside. So when I find this, this becomes 2xt plus y. Okay, I treated x and y as if they were numbers. Okay, they're not the thing that I'm dividing. So the same goes for dy over dt. Something like that. Whatever is in the denominator, that thing there is what I'm going to make the subject of my derivation. Okay, makes sense. If I take f derivative, it's what's inside here that I'm going to make the subject of my derivation. Make sense? Okay.